Section 29.6, the Heisenberg Uncertainty Principle. So a scientist named Heisenberg came up with the idea that we have a limit to how much we can observe something. And if we observe more about its position, we know less about how fast it's moving. If we know more about how fast it's moving, we know less about where it is. These seems really strange, and part of it is it's because it only is really observed when things are really, really small. But let's take a look first at Heisenberg Uncertainty Principle in greater detail. So for momentum and position, it's written that the uncertainty in the y component of the particle's momentum multiplied by the uncertainty in the particle's position along the y direction must be greater than or equal to Planck's constant divided by 4 pi. A couple of things here. First, the delta symbols here, the triangles, are here not referring to a change in. This isn't a change in y or a change in momentum. It's an uncertainty. So that's the key word to really focus in on, that it's really looking at uncertainty. And that's something that the problems will usually either give you in the description or ask you to solve for an uncertainty there. Also, it's greater than or equal to. In other words, there's a limit to how little uncertainty we can have. The uncertainty can always be bigger than h over 4 pi, but it must, the two uncertainties multiplied together must at minimum be equal to Planck's constant divided by 4 pi. So here's one example of the Heisenberg uncertainty principle with the uncertainty in momentum, the uncertainty in position. We can also write this uncertainty principle instead of momentum and position. We can write it instead in terms of energy and time, where we have uncertainty in the energy of a particle when the particle is at a certain state, and multiplied by the time interval during which the particle is in that particular state. And once again, that's greater than or equal to Planck's constant h divided by 4 pi. All right, so with this in mind, let's take a look at a conceptual example to see if we can try and wrap our heads around this just a little more. So what if Planck's constant were large? A bullet leaving the barrel of a gun is analogous to an electron passing through the single slit. With this analogy in mind, what would hunting be like if Planck's constant has a relatively large value? Would it be A, more accurate because of less uncertainty in where the bullet hits the target, B, less accurate because of greater uncertainty in where the bullet hits the target, or C, there'd be no difference? So I want you to think this through, come up with an answer, and then we'll continue. So go ahead and hit pause now. Did you do that? All right, well, let's think about it. The uncertainty must always be greater than Planck's constant, right? We have delta P times delta Y is greater than or equal to Planck's constant. So if Planck's constant becomes bigger, that means our uncertainty becomes bigger too, which in the horizontal direction perhaps isn't such a big deal. But if we think about in the vertical direction, if we send an electron through a single slit like as shown, it's going to gain some uncertainty in the y direction as it passes through, that electron going through the single slit could go straight through to the middle, or it could go to one side. If Planck's constant becomes larger, that means the uncertainty in how much the particle moves up or down changes dramatically. And that bullet may no longer pass in a straight line. So if Planck's constant had a relatively large value, I would not want to go hunting with you, is the short of it. All right. Let's see, example 6, Heisenberg Uncertainty Principle. Assume that the position of an object is known so precisely that the uncertainty in the position is only 1.5 times 10 to the negative 11 meters. Wow, that's super precise. A, determine the minimum uncertainty in the momentum of the object. Then find the corresponding minimum uncertainty in the speed of the object in the case when the object is B, an electron with the mass as shown, and C, a ping pong. a mass of 2.2 times 10 to the minus 3 kilograms. All right, so once we start hearing things about uncertainty, you want to think of Heisenberg Uncertainty Principle. It's almost always going to be the case. And here they mention position and momentum. So that tells us we want to use the version that has an uncertainty in momentum and uncertainty in position. And we're going to solve for when it is equal, because that's going to be the minimum uncertainty that we can have. We don't need the greater than, because it can always be bigger. We'll just use the equality there. So I'll divide my uncertainty in y to the right side, and then I just have Planck's constant divided by 4 pi divided by this uncertainty in the y component. And that tells me that the uncertainty in the y component of the momentum is 3.5 times 10 to the negative 24 kilograms meters per second, which are my units of linear momentum. Now, we know that momentum, assuming we aren't at relativistic speeds, can be calculated with mass times velocity. So that tells us if we have uncertainty in the momentum, we're going to also have some uncertainty in the velocity or the speed. The mass is going to be pretty constant, so we don't need to worry about that. So the uncertainty in the velocity will be the uncertainty in the momentum divided by the mass. That means for the electron, the uncertainty in the velocity is 3.8 times 10 to the 6 meters per second. That's a lot. That's faster than some of our examples with electron speeds. So just a small uncertainty in the y position of the electron gives a huge uncertainty in the speed of the electron. We got really precise with where the electron is. It means we know very little about how fast the electron is going. Now, for comparison, we can also do the calculation with a ping pong ball, which has a much larger mass compared to an electron. I know, not used to hearing ping pong balls be described as massive, but just another instance of everything being relative. We find that the uncertainty in the ping pong ball's velocity is 1.6 times 10 to the negative 21 meters per second. It's tiny. And that's part of why this idea seems so weird to us, because with things like ping pong balls, we know exactly where it is and how fast it's going. That's really easy to observe both of them. But for the electron, because it's so small, once we know very precisely where it is, it becomes very hard to know how fast it's going. Or you can know how fast you're going, but you won't know precisely where you are. So this introduces the Heisenberg Uncertainty Principle.